Hello everyone. Sorry for being late. My previous meeting was just finished. So let's see the topic today, graphs. Okay, for graphs, you will have a lot of visualizations to support your understanding. Because you will see all kinds of graphs. How we can use different graphs for different interests. Okay, so in this chapter, we will see what is graphs and different graph models, especially some different terminologies, how to describe the graphs. And then we will see how we representing graphs and a very special term, isomorphism, how to distinguish they are actually the same graph, but in different configurations. And then we will analyze different properties of graphs, such as connectivity. And then we will see Euler and Hamilton graphs to help us solve more difficult problems. Okay, section 10.1 to see different graphs types and graph models. Okay, so let's see the definition of graph. A graph G consists of a non-empty set V and E. So in this graph, we have different vertices. For example, A, B, C, D. And then we have edges connecting, for example, A and B. Then we have an H here. So if we collect all these vertices and all these edges, then we can create two different sets, V and E. Okay, so actually, if we define a graph G, then we can collect their vertex set and H set. Next, let's see, we have edges. So it can be connecting one or two vertices. In this case, we can see this edge connecting A and B, but in later text, we will see we may have the edge connecting over one vertex. And the vertex associated with it, we call it endpoint. And an edge is meant to connect its endpoint. Right? Next, let's see different types of graphs. The first one is simple graph. If we have the edge connect two different vertices and no two edges connecting the same pair of vertices, then we call this simple graph. Okay, in this case, we have the edge connecting A and B, right? So that means we have the edge connecting two different vertices. And then for the same pair, for example, AB, BC, and CA, we have no two edges for the same pair. So what is two edges connecting the same pair? That's the multigraph. For the vertex A and C, we have two different edges connecting A and C. So if we have more edges connecting the same pair of vertices, then we call this graph multigraph. And we say the number of such edges multiplicity n of the edge UV. In this case, the multiplicity of AC is 2, and the multiplicity of BC is also 2. But the multiplicity of AB is just 1. Okay, next we have a very special configurations of the graph called loop. Okay, because we can see there is a loop starting at B and ending at B. Okay, so that's what we call an H can connect to two different vertices, but it's one or more vertices. So if it just connect one vertex, that's the H what we call a loop. Okay, if we have a loop in this graph, then we call this pseudo graph because we may have multiple edges, we may have loops in this graph. Okay, so the first type we have simple graph, multi-graph, and pseudo-graph. Next, we can consider the attribute of the edges. If the edge has its own direction, if we have the direction for edges, then we call that directed graph. Okay, for example, we have the edge start at B, but end at B, start at A, A and B. So you can see the edge pointing to this edge. Okay, so if we have the ragged edges, then we call this graph the ragged graph. So for previous examples, we can call them undirected graph. All right. Now we can combine three different types by two different undirected or directed graphs. For example, simple directed graph. Okay, if we have no loops, no multiple edges, but the edge is directed, then we can call this simple directed graph. For example, A has an edge point to B, B has a point to C, or C point to B. So now you need to consider these two edges are different edges, because if one is B point to C and one is C point to B, so it's not multiple edges between B, C. So we consider they are two different edges. But if we have another edges point from B to C, then we call it semantic graph, because we have multiplicity of two from B, C, to C. All right. So first one, simple directed graph, and then we have the directed multigraph. For the following example, we have edges from A to C, and we have another edges from A to C, and we also have loops. Okay, so for the vertex B and C. Okay, so we call this the directed multigraph.我们在讲路谱的时候，实际上是这个点出发会到自己叫做的路谱，是 A 走 B 走 C。B 走 C， 再回到 B。那这个如果是起点跟终点都是自己，它的起点是 A， 终点是 C。起点是 B， 终点是 C。那这个 H 的起点是 C， 起点终点不一样。如果是自己出发回到自己。Alright, so next let's see a table to summarize different graph types for you. We have simple graph, if the edges are undirected, then we have no multiple edges, no loops. For multigraph, we have multiple edges but no loops. For supergraph, yes, we can have both. And then we have simple directed graph. So the edge is directed, and then we have no multiple edges, and we have no loops. We have multiple edges and loops. Okay, so you need to distinguish the difference between multigraph and directed multigraph. Because for multigraph, loops is not allowed. But for directed multigraph, we can have loops. The last one is mixed graph. We can have both directed and undirected edges within one graph. Okay, next let's see different graph models for example computer networks. So if we consider different data centers in different cities, and we have the communication links between this data center. For example, we have data center in San Francisco or data center in Denver. Then if we have a communication link between these two data centers, then we can use a simple graph to show the connection between each data center. Okay. If we want to represent more data paths between the data centers, for example, we have two different routes from Los Angeles to Denver, then we can use multi-graph to represent the computer. If we want to distinguish different upload or download links, then we can use the directed graph. Because for our network we have different data rate for downloading, right? So we may have directed edges from San Francisco to Denver and different edges from Denver to San Francisco. Then we can mark different data rate. Okay, the last one is the graph with links. Okay, we call this diagnostic links. If we can uh, if we have we can examine the data center by ourselves, then maybe we send the data and the destination is also itself. Okay, so we call this diagnostic links. So in this case, you can see the goal is to represent the computer networks, but we can choose different kinds of graphs or different graph models to represent the computer networks by our different goals. Let's see other applications where we can apply graphs to represent different situations, such as social network, communication networks, or software design. All right, the first one is for our social networks. Okay, so for example, friendship graphs. If you choose each different person in the Facebook website, and then we can see if they are friends to each other, then we can build an age for that two person. So the person is the vertex, and their friendship is the ages. Then we can build a friendship graphs. For example, if we have 40 students sitting here, and I'm not sure if you are friends with each other to all students. Okay. For example, if she and you are friends, then we have a link or age between these two groups. We call this friendship graph. Okay, except for friendship, we can also indicate collaborations or influence. For example, in the final projects, you, him, and her, you are on the same team. Then you have the relationship of collaboration. Then you can depict the graph of all students in our class, of which one and the other ones have the relationship of collaborations. Okay, and then you can also draw inference graphs between instances, which one because we call that influencer of IG, right? If you follow the influencer, then maybe we can draw a link or age between you and him. All right. Next, I want to answer this question: what type is best for best friend graph? Because previously we wanted to five or six different types of graphs. So if you want to draw the best friend graph, what type of graph you will choose? Maybe we can go back to the table and you can choose between these different types to consider which one is best choice for friendship graph, best friend graph. Maybe the first thing you can consider is it will be a directed graph or undirected graph. And then based on these two different categories, you can choose the submodels between that category. All right. Anyone want to share your answer to the other students? Okay. Please say that again. Directed multigraph. Okay, so what's your reason? Okay, maybe you can draw the graph or give us an example here. For example, we have 4 people.
Yeah. So B is A the best friend, and we can have C
And D, because we have 4 different persons.
好像是 simple，
Okay, you can modify your answer, it's okay. So, what's your answer?
应该是 simple。
Simple directed graph.
Yeah, sorry.
Okay. Okay. So if you choose simple directed graph, that means multiple edges or loops are not allowed. Okay, so let's see why multiple edges is not allowed. Because we are mentioned best friend, right? So you cannot choose 2 friends as your best friend. Can we? Really? Can we have 2 best friends in my life? Oh, no. I mean, I have 2 best friends. A and B, they are both my best friend. Is that okay? Okay, so we need to clearly define what is best friend. If we have only one best friend among all my friends, then we can just choose one. But if multiple best friends are allowed, then we can choose multi-graph. Okay, the second question is loop allowed for this problem? Can me be my best friend of myself? The other person are not friend of mine. Me are my best friend. Is that okay? Okay, it's not defined. Okay, so we need a well definition for best friend. Maybe someone will claim that he is the best friend of himself. Okay, so we don't have a correct answer here, but I want you to consider the problem and choose a proper graph model. Okay, 1 extra point. All right, let's see more examples of social networks. If we can connect their friendships or influence, then we can see for influence graph, maybe it's one way it's connected. Because Brian and then we have the example of Hollywood graph or academic collaboration graph. For example, different actors, they collaborate within the same movie. Then we can build an age between these 2 persons. All right. We also have web graph. For example, when you click into the website, you will see the structure. Most of all, they are 3 structures of the website. We have the main page and different subpages. Okay, that's web graph. And when you write papers, you may have citation graph because usually the academic paper has a lot of reference papers. Okay, so if we have paper A, B, C, D, E, F, then we can see maybe paper A reference paper B, C, D. Then we can build this citation graph. Of course, for transportation, we have airline networks or road networks. If we consider different cities as the vertex and different airline routes as the edge, and then we may have the graph like this. All right. We also have software design applications. For example, we can have module dependency graph. For example, when you build a system, you have the main program, and you have different sub-modules, such as display module, parser module, and protocol modules. For each module, we have different functions. For example, pages or networks. So in this case, we can see in order to extract the correct syntax tree, custom module. So we call this module dependency graph. All right, and then we can also have precedence graph for example, assembly language. Because for assembly or for computer programs, we have different variables. And when we need to calculate the values for variable E, then we need to calculate C first. And to calculate C and B, we need to know the value of variable A and B. So in this case, we can build such precedence graph to see which variable or which register will be used first and their dependency. Okay, for animals, we have biological graphs. If they compete for the same kind of food resources, for example, raccoon, hog, and all, they compete for the food such as rats or insects. Okay, and we can do the age between that two different species. All right, the last one is protein interaction graphs. If we have different proteins, such as RRP43 and the other proteins, once they have the function of interaction, then we can build an age between different proteins. Okay, so this is section 10.1. We have seen different types of graphs and where they can apply to different kinds of applications. Let's see some definitions of graphs. We have different terminologies and some special types of graphs. Okay, the first definition is adjacent. If we have two vertices in undirected edge, they have the edge to connect vertex U and V. Then we call this vertex U and V adjacent vertex. Okay, and if we have an edge connecting to U and V, we call that HE is incident with vertex U and V, and E is connected to U and V. Okay, so next you see these keywords, adjacent, incident, and connect. You will see how this graph is configured. Okay, next definition is the neighborhood. Okay, if we consider all vertices connecting to some vertex V, then we can collect all adjacent vertices into a set. We call that the neighborhood of V. Okay, then we can also collect a subset of neighborhood vertices. If we have a V in this subset A, and we collect all this A of V and apply the union operations, then that will be the union of neighborhood subset A. Okay, the third definition is degree. A degree is a vertex. How many edges incident with that vertex? We call that degree of that vertex. Okay, so maybe we can see the example here. Okay, here we have two graphs, simple graphs and multi-graphs. Let's see, the degree is number of edges incident with that vertex. So if we consider the degree of vertex A, here we have two edges incident with the vertex A. Okay, so the degree of A is 2. Right? Then maybe we can consider multi-graph or graph with hooks. For example, we have the vertex B. So how many edges incident by the vertex B? 1, 2, 3, 4, 5, 6. And if we have the loops, then we can count twice for this degree. So the degree of B is 6 in the multi-graph. And then we can consider the neighborhood of A. Okay. So if we have two edges connecting to A, then the endpoint is the neighborhood of point B in this multigraph. So we know we have A, E, D, C, and by this loop, B is also the neighbor of the vertex P. So if we consider the neighborhood of B, we have A, B, C, D, E. Next, let's see the theorem of degree. So we call this handshaking theorem. If we have the graph G, then the summation of all vertices in this graph, if we calculate the total summation of the degree, then it equals 2 times n. N is the number of edges. Okay, so we know the reason because when we calculate the degree of between the vertex A and B, for example here. Okay, so when we calculate the degree of A, then we count this edge once, right? But when we calculate the degree of the vertex B, we count this edge again. So each edge will count by 2 endpoints twice. So in this case, if we calculate the summation of degree A, degree B, degree C, and add them all together, then every edge will count it twice. So the total number equals 2 times n. Okay, so it's very like handshaking by two friends, right? So if the friends are vertices and their hands are the edges, then we will count the degrees by these two people twice. All right, then by the theorem, we can see the following example. How many edges are there in a graph with 10 vertices of degree 6? Okay, for example, we have a graph, all their vertices are degree 6. And totally, we have 10 vertices. Then how many edges? By the handshaking theorem, if we calculate the summation of the degree of all vertices, then that will be 10 times 6. And the total summation will be 60. And it equals 2 times n. Okay, so n is the number of edges. So the number of edges will be 30. Okay, next example, if a graph has 5 vertices, okay, each vertex has degree 3. Okay, so by the handshaking theorem, we can see the summation of the degree of all vertices will be an even number. Okay. So once we have 5 vertices and each has degree 3, then the total summation will be 50. Okay, then it's not an even number, so it's not possible. Okay, next, let's see an extended theorem. And on the rectangular graph has an even number of vertices of odd degree. Okay, so basically we can consider the vertices of even degree and odd degree. Are they even or odd? Okay, so let's see theorem 1. When we calculate the summation of the degree of all vertices, basically we can separate the two even degrees and odd degrees. For example, for the first category, they are all even degrees. So we have 2 plus 2 plus 2 plus 2. And then for the second category, their degrees are all odd. 3 plus 1 plus 1 plus 5. But we know the summation of these two numbers, actually they are even numbers. So we know the summation of even numbers, still even. But we need this total sum to be even as well. If this number is odd number, then odd plus even will not be an even number. Okay, so how to make this number even? We need to have even number of odd degrees. Okay, for example, if we have the number 2 for vertex B, then 3 plus 1 is 7. If we have 3 plus 1 plus 1 plus 5, the total number is 4, then the number is still even. But we cannot have odd numbers of odd vertex with the odd degree. So that the figure 2 tells us. All right, next let's see some discussion about the directed graph. Okay, so now we define the name for the edge of the directed graph. If we have the edge U, then that means we have the initial vertex U and terminal vertex V, then we can define an edge UV. So this is directed, so we need to know where it starts and where it ends. Okay, so we can use an order pair to indicate the edge of the directed graph by using a UV. Right? Next, let's see how we calculate the degree by directed graph. We define in degree and out degree. Okay, in degree is the number of edges which terminates at V. Okay, so that means how many edges come into the vertex V. Okay, for out degrees, the number of edges V as their initial vertex. They are going out of to other vertices. Okay, so maybe we can calculate the in degree and out degree by this example. For example, in vertex A, in degrees terminate at A. So we can see one edge terminate at A. This edge terminate as A. So the in degree of A is 2. And then for out degree, this edge going out of the vertex A. Or we can say it has A as its initial vertex. So 1, 2, 3, 4. Okay, so we have out degree of vertex A equals 4. Then we can apply the previous theorem again, because previously we have undirected graph, so we are not separating the summation of degree of vertex by in degree or out degree. But here we can see theorem 3, we have the summation of in degree equals the summation of out degree equals the total number of HE. Okay, it's very intuitive, right? Because for the HE, we can see this H actually is the out degree from 1 by A, and then it will come to in degree C. So we have the equal number of in degree and out degree for all the vertices in this graph. All right, next let's see some special type of simple graph. The first one is called complete graph. If we have n vertices in this graph, then we have edges between each pair of the vertices, and the number is exactly one edge. We call this complete graph. For example, we have 3 vertices, and for each pair of the vertices, we have an edge connecting this to a vertex. Then we call this complete graph. When we have 4 vertices, 5 vertices, and 6 vertices, we need to ensure that each pair of the vertices, where we have one edge connecting these 2 vertices, we call this complete graph. All right, next one, cycle graph Cn. That means we have n vertices in this graph, and we form a cycle. Cycle means you can start from arbitrary vertex and travel all other vertices and go back to itself. So we call that a cycle. So in this case, when we have 3 vertices, 4, 5, or 6, we can build a path. Then we call this graph a cycle graph. Next one, the wheel. Okay. So based on the graph cycle, then we can add one additional vertex in the middle, and then we connect the edge from this additional vertex to all the other vertices. And it's just like the wheel of your car or the wheel. Okay? So we use Wn to indicate the number of vertices in the cycle, but we didn't have one additional vertex in Wn. Okay, so you can see W3 actually is based on cycle graph V3. Okay, next one is n-dimensional hypercube, Qn. Okay, so for Qn, actually we have 2 to the power of n vertices. For example, 2, 4, or 8. And we have 2 to the power of n minus 1 times n edges. So you can see the connection of this vertex. Okay, and then there is one thing very special because we can use hypercube graph to represent all these strings of length n because when we have an edge connecting two vertices, then they have one bit in the position which are different. For example, for Q1, we can label 0 and 1. They have one bit difference. Then for Q2, we can label 0, 0. And the other end of the edge is 0, 1 or 1, 0. You can see we only have one bit difference between 1, 0 or 0, 1 to 0, 0. Okay, so actually you can expand this graph. For example, when we have Q1, then you can double Q1. For example, you have first Q1, second Q1 here. And then you connect the corresponding vertices to form Q2. And then for Q3, you can use first Q2 here. Okay, maybe we can consider the starting bit is 0. Okay, so this is the first Q2. This is the second Q2, starting the bits by 1. And then we connecting the corresponding vertices. Then we can build Q3 from Q2. Alright, so this is the simple graph hypercube. Now I would like to draw the graph of Q4. Please draw the graph on your A4 paper. What Q4 looks like. And you also need to label the bit string of Q4. All right, if you know how we process Q2 from Q1 and how to use Q2 to build Q3, then you will know how to build the Q4, right? All right, let's see. If we have Q1, the label is 0 and 1, then we can have two Q1 to build Q2. For example, this is the first Q1, this is the second Q1. And we know the label is 0, 1, 0, 1. But now it becomes Q2, so we need one bit more. So if starting with 0 and starting with 1, then we can connect the corresponding vertices because they are all 0, they are all 1 in the original Q1. Then that's how we build Q2. And then how we build Q3 by Q2, you can double the graph of Q2. So it will be 1, 0, 1, 1, 0, 0, and 0, 1 again. Now we have the corresponding point, all right? 0, 0, 0, 0, they are corresponding points. So we can build an edge between the corresponding points. And then we add one bit more to indicate they are from a different Q2. So we use 0 and 1 as their starting bit. Then that will be Q3. Okay, can you follow this process to build what is Q4? All right, if you want to build Q4, then you need the 2 Q3. Okay, so you need to draw Q3. And you need to double Q3, right? And then you need to add edges for corresponding vertices. For example, this one to this one, this one to this one, and this one to this one, this one to this one. And you need to include all corresponding edges. And then you change the original bit string of 0, 0, 0 to by one bit in front. For example, the first Q1 you pick is starting bit 0. And for the second Q3, you can start by bit 1. Okay, then they will have just exactly one bit different. Okay, is this okay? All right, next let's see some special case for computer network architecture. So when you take the course computer networks, you will see different topologies of computer networks. For example, you will see star topology. So in this case, you will see in the center we have a computer server. Then we have different terminals connecting to the server in the middle. And you also see ring topology. Okay, so one connect to one sequence and it forms a circle. Then we call this a ring topology. But they are considered to be very weak connections because once these connections fail, then we cannot communicate between these two systems. Even for real topology, it's still weak because once this link is broken, then you need to travel very long paths to set data to neighboring data center. So now we can combine these two topologies by the weak. Okay, so if you use this topology with this, then we can have a ring outside, and we can have a wheel at the center of the server in the middle. Okay, and then for computer networks, we have another architecture which is called a mesh. Okay, it's very common in parallel processor. It's usually in the topology mesh. All right. right, next graph we will see bipartite graph. So let's see the definition. A simple graph G is bipartite if V can be partitioned into two disjoint subsets V1 and V2, and every edge connecting a vertex in V1 and a vertex in V2. So maybe we can see this example. Okay, if we have now this is a cycle graph with 6, and then we can label the vertex 1, V2, V3, and V6. And then you can see for one edge, in V1 and V2, we need to partition different category. Then V1, we can contain V1, V3, V4. And the second category, we have vertex 2, V4, and V6. So in this case, we can bipartite the vertex into two disjoint sets, V1 and V2. Then we can call this one graph bipartite graph. Alright, so maybe we can check if V3 is bipartite. If we have V1, V2, V3. So if V1 in first category V1, V2 in the second category, then V3 we cannot distinguish because it's connecting to V1 and V2. So we cannot place V3 into either groups to make it a bipartite graph. So V3 is not a bipartite graph. So actually, we have another section to introduce the topic, how to coloring a graph. So if we consider the first vertex in the graph, we color by the red color. And then for the other vertex of the edge, we color by blue. Okay, then you can repeat this session to see if this is a bipartite graph. Because once C is blue, then the other edges connecting to C should be red. Okay, so now we can see B and E should be red. And then the other vertex, which connecting by the H to B, should be colored by blue. Okay, then you can repeat this process again until you can color all the vertices in the graph. If there's no contradiction, then we can see this is the bipartite graph. All right, next let's see another definition of complete bipartite graph. We use the notation KMN. Okay, MN means the number of vertices in the disjoint set V1 and V2. We have M vertices for V1 and M vertices for V1 and N vertices for V2. So if we have K, that means for the first set we have 2 vertices. For the second set we have 3 vertices. And we have all edges between the pair selecting from first category and second category. So we call this complete bipartite graph. All right, so you can see the applications of bipartite graph. We can match jobs or marriage. Okay, so in this case, you can see we have the name of our employee, and we have different tasks. Okay, so you can use bipartite graph to indicate who responsible for different tasks. In this case, we have refinement, application, testing. And then you can see for architecture design, we have Berkowitz and we have Chen responsible for this task. You can also draw the marriage bipartite graph. So because for marriage we need 2 persons. Okay, so the first category and second category we choose 1 vertex, and we use the H to indicate they get married. All right. Lastly, we have new graphs from old, how to build new graphs from the current graph. We call that subgraphs. Okay, so if we have the graph G, so a subgraph WF, okay, if W is the subset of V and F is the subset of E, then we call this graph is a subgraph of graph G. Okay, next we can see we have a complete graph defined. Now you can arbitrarily select the vertex and the edge to form the subgraph. For example, you can choose vertex A, E, C, and you can choose the edges T. And this will be one possible subgraph of K5. Alright, next let's see the definition of induced subgraph. So let's see the definition. If we have the subgraph WF, then the H set F contains edges in E, it can only give both endpoints R and W. So that means if you already choose the endpoint in W, then you must choose the H. Okay, so in this case we can see if we choose A and E in the subgraph, then you must choose this graph. So in this case, we can see actually we already select C and E. So in induce the subgraph, you must choose the H here. So you can see for induce the subgraph, you can arbitrarily choose how many vertices. But once you choose the vertex, then the H set is defined. Okay, you cannot choose arbitrarily vertex and arbitrarily edges, just like the original definition of subgraph. Is that clear enough? All right. Maybe we can have a practice here. Let's see if we have K5. So just draw the subgraph and induce the subgraph. If you choose the vertex different answer by these two subgraphs. So our definition, if we choose the vertex and what kind of subgraph we can draw, and what is the subgraph. All right. Anyone want to draw the subgraph and use the subgraph for 1 point? Okay, please. All right, very good. Thank you. Okay, so if we choose the vertex A, B, then you can choose arbitrary number of edges. In this case, we choose A, B, and A, B, the subgraph. Of course, you can choose only A, B, or A, E, or B, E. But for induced subgraph, once you choose A, B, E as your vertex in induced subgraph, then you need to choose. If they have edges in K5, then you need to choose that edge in the induced subgraph. So you must choose A, B, A, E. Okay, that's the difference from subgraphs and the induced subgraph. All right. Next, let's see how we derive new graphs. Maybe we can by different operations such as union. So in this case, we have two simple graphs G1 and G2. Then we can apply the union of G1 and G2. That means we have union the set of V1 and V2. And then we can also derive the union of G1, G2 under this operation. So let's see, we have G1 here, we have G2 here. So for G1, we have A, B, C, for G2, we have A, B, C, D, F. After the union operation, then we union the vertex set. So in this case, we have A, B, C, D, F. Okay. And then we also union its edges. So we combine all these edges in G1 and G2. And we have the union graph from G1 and G2. Okay, very simple operation. All right, now we have one exercise left. Okay, so count the number of subgraphs in K3. How many subgraphs in K3? All right, I will give you 2 extra points. If you can answer the total number correctly, and then you can draw all of the subgraphs of K3. Okay, remember for subgraphs, you can arbitrarily choose the number of vertices and the number of edges. Okay, so if in this case, we label the vertex ABC. Okay, just use this case. Okay, now we have to label ABC for this vertex. And how many different subgraphs will we have? All right. Do you have the answer yet? Okay. How many? 11. Okay. Please draw your answer here. Why we have totally 11 subgraphs of K3? Okay. Please erase all of this. And let's see how you consider the number of subgraphs. All right, he just choose different vertices, for example, A, AB, or AC, or ABC. All right, then we have 4 subgraphs. And then he add edges between this vertices. So we have edges between AC, AB, and okay, now we have different number of vertices. If the total number of vertices is 2 or 3. All right, so what's the total number? 13. All right. All right, thank you. So could you draw more subgraphs than his answer? Okay, please. Okay, so let's try. Okay, you think it's 17. Why? Okay, so let's see. For the first case, if you choose only one vertex, then his answer will be A. But you can also choose B or C. So the total number of only choose one vertex, we have 3 different subgraphs. And then, okay. Okay, no, wait. Okay, so if you choose 2 vertices without edges, then we have 3 different choices: A, B, A, C, and B, C, right? No, not yet. Because you can also choose 3 vertices. You can choose 1, choose 2, choose 3. Okay, so we have 1 subgraph. So if you choose only vertex and no edges, then totally we will have 7 different subgraphs. Okay, and then what's next? But we already have no edges in the previous case. Okay, so how many subgraphs if we have edges between 2 vertices? 6. Why? Okay, so I mentioned if you choose AC, because we have AC, AB, and BC, we have no edges. Now if you add edges, then the total number will be 3, right? Is that right? But you say different numbers, right? 所以取2个点再加边的种类有几个？好，6个好，所以加的边是3个，不加边也是3个嘛，好，所以这边总共就是有6个。Okay, what's next? 然后取3个点的，因为你可以选的那个，他们点的点是所以它会是1、2、3，你有2乘3，在2的3次方。Okay, so you can add 1 edges or 2 edges. So if you add 1 edges, then the number will be 3. If you add 2 edges, it will be also 3. Is that right? 就是3个点，你要加边，总共有几种？你直接告诉我几种好了。好，那你讲一下哪8种？OK， 我知道了啦，3加3是6嘛，然后全部不加边1种，全部加边也是1种，所以是6种。OK. All right, so is that all? So what's the total number so far? All right, so anything missing? All right, okay. So please verify this exercise by yourself when you go back home. Okay, so now I want this to be a homework assignment. and you need to submit your final answer before next class. Okay. Let's draw this by yourself and give me a complete answer. How many numbers? And draw this subgraph by yourself. Okay. See you next time.应该不止吧？对，我再确认一下，还缺了哪些？这样，再回去画画看就好了。
这个不是就是选点跟选边？
没错，就是选点选边而已。
可是我这选点不是最多是3个，点跟点之间连接，就我先用分层分1个、2个、3个，然后再看要不要连，这样子就是17不是选一个点 C31嘛，这样是3个，选2个点是 C32，然后2个点之间有线可以连接，你可以要连或不连，所以是 C32乘以2，然后选3个点 C33，然后再乘以2个点之间有线，所以因为它有连接3条线，所以是要连或不连是2的3次方，这样不是17种。
我们刚刚算出来17种啊。
还有多少？
我再确认一下哦。好。好，怎么样？你有什么问题？
他说他要确认一下。那这样可以加分吗？
可以啊，可以，你可以加分，好，找助教加分。
好。
你觉得是17，你就submit 17这个答案了。这是我们的作业啊。
然后我上次有请假。然后
有被点名是不是？
对。
然后呢？
可以帮我通过吗？那个。
当然不行啊，你又没来。
不行吗？
你又没来，怎么能帮你算通过？
可我请心理假。
那你就是给学校的假单，你只要有学校正式假单，我们就不会算缺席。
可是我那个是线上的。
那你总要有证明嘛，请假的证明，无论你给什么样的学校的证明，纸本的、线上的都可以啊。你就寄你的请假的证明给助教，我们就不会算缺席。
好的。好。
好。对，我们会。对，会，对，我们会提早公布小考。
这个是假题，我刚回答。
这个本来是给同学，对不对？好，但是因为同学已经前面回答过一遍，你帮他补充剩下的这样，我们就这样子好啊。好。